All right, so here we are with lecture 1.2. Starting off with integer exponents and rules for working with exponents. Okay, so at this point we've worked with exponents before this class. You should have had some experience working with exponents. So let's take a look at this problem. We're asked to simplify. There's an ant. Okay. So normally what I'll do is I'll look inside the parentheses and see if I can simplify anything first between the numerator itself and the denominator, and then see if I can simplify through the whole fraction. So looking at the top, do I see any common bases there? I have an a, b, and a 2. No like bases there, I can't simplify the top. How about the bottom? A, b, and a c. Still, none of them are the same, so I can't simplify on the top or bottom. So let's look at the whole fraction. I see an a on the top and an a on the bottom, so I know I can simplify those. I also see a b on the top and a b on the bottom. So I'm going to go ahead and work with simplifying those. So 2a b to the negative 1. I'm going to rewrite this so you can kind of see the variables on the top and bottom of each other. All right, so there we go. So now what I'm going to do is use the quotient rule and rewrite this. So I have 2a to the, that's a 1 power, 1 minus 3. So we used the quotient rule and did the 1 minus the 3. Let's do the same for b. It's b to the negative 1, and then using the quotient rule would bring up the 2, so b minus 2. All right. And still on the bottom, we have our c to the negative 3 power. Let me change that parenthesis right there. That's kind of ugly. Okay. All right, and here's my arrow to indicate where I'm going with my work. Equals, let's simplify this. So we have 2, and then 1 minus 3 is going to be a negative 2. And then b to the negative 1 minus negative 2 is going to be b to the negative 3. Then we have c to the negative 3 on the bottom. The negative 2 power. Okay, so we've done everything we can to simplify the inside. So once we've done that, we'll bring that negative 2 exponent in using the distribution rule. So everybody gets the negative 2. Okay, we're just distributing in that negative 2, and we can do that because it's all multiplication going on inside. If there was addition or subtraction, we couldn't do that. But because of the multiplication, we can go ahead and distribute the 2 to everybody. Okay, once we've done that, now we have a bunch of power rules going on. So I'll just leave the 2 to the negative 2 for now. And then we multiply the negative 2 times negative 2, and we'll get a positive 4. And then b negative 3 times negative 2 is going to be b to the 6th power, and then c to the 6th power. All right. Now, when we're working with exponents, once you've simplified so that there's only one of each base, so notice we only have 1a, 1b, 1c, and 1, 2. What you want to do is make sure that there are no negative exponents hanging around. So I see this negative exponent here with a 2, so I'm going to use the reciprocal rule and bring it into the denominator. Okay, so real quick, let me rewrite what it would look like before I did that. Okay, using the reciprocal rule, I'd get 2 to the positive 2 power. And then I can re-multiply out again. You don't need to do this whole step where I've split the fraction. I'm just showing you how the reciprocal step works. Okay. And in fact, when I do that, instead of rewriting 2 to the 2nd power, I can just multiply that out, and that's going to be 4. And there we go. So best thing to do first is look inside the parentheses and see if you can simplify. And once you've done all the simplifying you can, then you'll bring in that exponent from the outside. And lastly, make sure none of your exponents are negative. Okay. There's one instance when you're allowed to leave your exponents negative, and we'll get to that shortly. Okay, we're going to do a quick proof. So this is a law that we know a lot for rows of exponents. If you have the same base, a to the m times a to the n, what you can do is say keep the base and add the exponents. Okay, so we're going to go ahead and prove this. This is called the left-hand side, and this is the right-hand side. So let's go ahead and we're going to prove using the left-hand side first and show how we get the right-hand side. So a to the m, what does that mean? Well, that means we have a times a times a m times. Okay? And then after that, we're multiplying that by a to the n. So that's a times a times a, however many times, well, n times. Okay? So that means in the end, we have a times dot, 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 times a, dropping this inner parentheses. We can just multiply the other ones together. So how many a's do we have? Well, we have whatever n is plus whatever n is. So m plus n times. And rewriting that, we can say we have a to the n plus m. And there we go. This is the right-hand side. So my proof is done. And we fill in the little box there. Some people like to do the box, some people do the little 3 dots, or some people use POW. Up to you to indicate when you have finished your proof. All right. Moving on. So scientific notation. All right. So scientific notation is normally when we're trying to make a really large number look a little simpler, or a really small decimal look a little simpler as well. And let me get rid of that bug. Okay. So they want us to write 0.0045 into scientific notation. So just a reminder, for scientific notation, you rewrite it so you have your number b times 10 to some power n. Now this is the one time when we're allowed to leave our exponent negative. So the number here for n, that could be negative. Now we have a restriction for b. So b needs to be between 0 and 10. Okay? 0 and 10. Cannot be bigger than 10. All right. So, at the moment, with our number 0.0045, is this number between 0 and 10? Oh, sorry, not 0 and 10, 1 and 10. Rewrite that one, 1 and 10. Okay, so no, this number is not. Okay, so what we need to do is if I move the decimal over once, it's still too small. If we move it over twice, once again, it's still too small. How about let's move it over one more time? Is the number 4.5 between 1 and 10? Yes, it is. So it should be equal to right there. Okay, so I know that the number 4.5 works. But careful. Because I moved the decimal over, I need to balance that out with something. I moved the decimal over how many places? 1, 2, 3 places. Okay, so we're going to write this as 4.5 times 10 to the. Now we moved it 3 places, but we have to be careful. Is that positive or negative? Okay, a way to remember it is if your number started out as a small little decimal, think of it in terms of money. In your bank account, if you saw a teeny little decimal, that would be a very negative experience to see in your bank account. Okay? If you saw a huge number in your bank account, that would be a positive experience. So, since this is a teeny little since this is a teeny little decimal, that's a negative experience. So, it was originally a decimal, and therefore it's going to be a negative. Okay? That's the way I just like to remember it. If you can just remember it without that, go ahead. Up to you on how you can memorize these things. Okay, so we wrote 0.0045 into scientific notation. We moved the decimal until we got our number in between 1 and 10, which is how we got 4.5. And since the number was originally, this ant will not give up. Okay, since the number was originally a small decimal, wow, he's back. Let me restart that. So we had 0.0045, and we're trying to write this in scientific notation. So to do that, we had to move our decimal a number of times until we got the number between 1 and 10. Okay, and then we multiply that by 10 to the number of times we moved our decimal, which is 3. And since our number was originally a small decimal, we'll use the negative. And there we go, scientific notation. Okay, so now, example 4, we're going the opposite direction. Okay, so we want to write this as a decimal. Okay, so the thing I want to do is take a look at the exponent on the 10. This will tell me how many times to move my decimal, as well as the direction. So the 5 tells me I need to move decimal 5 times. I need to look at the sign now to determine which direction to move, either to the right or the left. Now remember, if it's a negative, that means my problem was originally a decimal, a small decimal number. Okay? So, that means we're going to be moving to the left. All right, here we go. Let's start with 1.06, and we're moving to the left how many times? 5. 1, 2, 3, 4, 5. Boop. Okay, let's fill in those places with zeros. 1, 2, 3, 4, and the extra 0 there. Okay, and there we go. If you want to clean that up, that is our number, written as a decimal. Okay, that was page 1. Let's go ahead and look at page 2. Example 5. Simplify and write the final answer in scientific notation. Okay, so let's take a look at this. I have 3 scientific notation numbers. Okay, and one thing to remember, that's a times symbol, that's a times symbol, and that's a times symbol. Those are not the variable x. So what I like to do is I'm going to rewrite this problem using just the multiplication symbol. Okay, so this times 10 to the 6th times 2.4 times 10 to the negative 8 all over 8 times 10 to the 5th power. Okay, once I've done that, notice these are all just multiplications. So I'm going to go ahead and rearrange the top so the 10s are near each other and the numbers are near each other. Okay, once I've done that, now I will multiply together these two numbers. And what do I get? Let's pull out the calculator. Can you see that? 3.2 times 2.4 is 7.68. Okay, rewriting that over here, using my arrow to indicate where my work has gone. What did I say that was? 7.68. All right, and then notice, right here, we have rules of exponents going on. Keep the base and add the exponents. So the base is 10, and we're adding the exponents 6 plus negative 8, which is going to be negative 2. And on the bottom, we still have that 8 times 10 to the 5th power. Okay, so now what I'm going to do is focus on the number parts together, and then the exponent parts. Okay, so let's take the 7.68 and divide that by 8. What do we get? 0.96. 0.96. Okay, and then right now we can use the quotient rule on the 10s. So that's going to be times 10 to the negative 2 minus 5. Going ahead and simplifying that, I have 0.96 times 10 to the negative 7. Okay, so we might be tempted to say we're done and it's in scientific notation. But one thing to note, first, we need to use the x symbol in scientific notation. Okay, so we're going to go ahead and add that in. Okay, and we're almost there. Remember, the number here needs to be between 1 and 10. And 0.96 is not between 1 and 10. So I need to move the decimal over. So I'm going to go ahead and move the decimal over once. And now I've created a number that's between 1 and 10. But because I moved the number, I need to go ahead and add 10. I move the decimal once, and the question is this a negative or positive? Well, I just made the number this direction, so it used to be a small number, so that's going to be a negative, because it used to be a smaller number. Okay, so now let's see what we have. I have 0, 9, I don't need the 0 anymore. I have 9.6 times 10 to the negative 7 times 10 to the negative 1. Simplifying, I can get 9.6 times 10 to the negative 8. And there we go, let's check. Do I have the X symbol? Yep. Do I have the 9.6 that's in between 1 and 10? Yep. Oh, am I allowed to have a negative? Yes, remember we're allowed to have a negative if we're using scientific notation. So this answer is good. All right. So now we're moving into radicals, the crazy numbers. Okay, so we have this right here. The square root, or the nth root of a equals b means that b to the n power equals a. Okay, so if n is an even value, then a and b need to be greater than or equal to 0. Okay, so here's a question. Why do we need the condition if n is even, then a and b are greater than or equal to 0? Try to think on that for a second. Well, here's an example. So let's think of one where n is even. So how about the square root? I'll think of two examples. I'll pick an a value greater than 0, so 4. Does that work? Is there a number times itself that can give me 4? Yeah, 2 times 2 gives me 4. Okay, so that works. This would be my b value, 2, and the 4 would be my a value. So they're both greater than 0. Awesome. What about if I picked an a value less than 0? How about negative 4? This is saying, is there a number that times itself would give me negative 4? Well, 2 times 2 gave me positive 4. What about negative 2 times negative 2? Does that work? No, because when I multiply a negative times a negative, I should be getting a positive, not a negative. So this doesn't work. I can't do this with my real numbers. Okay, so we need the restriction that a and b are greater than 0 if n is even. Okay, so if your radical value is an even number, for example, 4th root, 6th root, and so on, you need to have the numbers on the inside to be greater than or equal to 0. All right. Okay, so example number 6. We're going to go ahead and simplify some radicals here. So now this is interesting. Notice I have a negative under the radical. Is this a problem? Well, let's see. It's talking about the cube root, so it's asking, is there a number that exists that when you times it together 3 times, you get negative 27? Yes, there is that number. Negative 3 times negative 3 times negative 3. Because negative times a negative is a positive, but then a positive times a negative would give me back that negative. So it's okay to have a negative if you have an odd radical. Okay, so cube root of negative 27 is negative 3. All right, so here we go. Square root of negative 4, does that work? We kind of just did this. Is there a number that times itself gives me negative 4? The answer is nope. Okay, so this one would be, the answer would be not a real number, or you could put an imaginary number, but for now we're going to say no solution, or not a real number. Let's take a look at C. So this is saying, is there a variable times itself gives me x squared? Yeah, there is. X times x. Okay, so one way you can do this is you can go ahead and say, when you see the square root and the 2, sometimes you can just, it's a simple way of doing it, say they cancel each other out. But this is really what's happening there. Okay, you're finding a number that times itself equals x squared. So the answer here is x. Okay, D. It's getting a little more complicated here. So the fourth root of 16 times x to the fourth. So what we're going to do, this concept we used here about having something raised to the same power as our radical, we're going to try to do that here. I want to get the inside to be the same power as my radical. And then I can sort of cancel them out if you want to say that. Well, the x to the 4, it's already got a fourth, so we can write that down. The question is, can I rewrite 16 as something to the fourth power? Is there a number that times itself 4 times gives me 16? Yeah, 2.